So let's go through the lesson 15 key here. Number one for the free body diagram. This rock wasn't moving, right? Fn and Fg must be balanced, right? There is an Fg and there is an Fn, but they have to be balanced. If they weren't, it would be accelerating upward or it would be accelerating down through the earth. Okay, B, these must all be balanced too because it's not moving. So you can just label, yeah, those like that. Rock is falling. That's one you might think of because it's like, accelerating downward, and that's kind of follows your intuition. So it's going to be a force just downward. Rock is falling with some air friction. Well, yeah, so it's still falling, and then there's the force of friction is pushing back up. Rock falling at constant terminal velocity. So terminal velocity means that, yeah, like the air resistance is matching the force of gravity. So when that happens, the force of friction is balanced with the force of gravity. There is no net force on you, right? So that's why you're not accelerating. You're falling at a constant velocity. Okay, this one, they did a study on this one where they asked a whole bunch of like adults what their intuition about this one was. Most people would think that if this thing is rising upward, it must be like accelerating upward and then like, accelerating downward at that point. But the force on this thing is down the entire time. The only force here is the force of gravity. What other force is there? Like nothing is pushing this thing as it's going up, right? It's just this thing's momentum is just carrying it forward, or its inertia, I should say, terms that we've covered. Okay, and then even here, same thing, just straight down. This entire path of this thing, there's nothing else other than gravity pushing on it or pulling on it. So most of these questions are pretty, like, not easy, but I think from the key here you can get what you should have done, right? I don't think I need to explain all of them, especially these first few. So take a look at those, see what you did right or what you did wrong. I'll do number 7 though, or talk about it anyway. So it says, and actually, well, let's read this first. So it says, car of mass 1.5 times 10 to the 3 kilograms is being driven at 20 meters per second. The car sees a massive hole 100 meters ahead. What's the minimum friction force required to stop the car in time? Okay, so actually just kind of you can ignore this part. I don't really, yeah. So we have this info. So the key bit here was that V2 or VF was equal to 0. We had to figure out the acceleration. And our net force here, we're going to assume that the entire like the frictional force is the net force. So if we figure out A and then just put it into this formula, we can figure out the net force required is negative 3,000 newtons. It's number 10. I'm going to skip a few here and go to number 10. So this is our situation. So it was saying that we have 10 newtons going up, 15 newtons pulling to the left, and we have to figure out what this force is. Well, in order for this to be balanced and not be moving, the x component of this thing and the y component of this thing have to equal the two up here. So that the y component of this force must be the same in magnitude as the y component of that, or the y, because that's all y. And then the same with the x component. The x component has to be the same as that, just different directions. So if you just figure out this triangle like we've done before, you get this answer. Okay, number 11. That was actually a lot like the practice problem that I did, right? So it's one of those ones that you have to break it into its components, make a new triangle out of those components, and then figure out the magnitude and your angle of that, and then use that to figure out acceleration. So pretty much just like the one we did in the practice problem, so I won't go over that. Number 12. Nope, wrong one. Yeah, number 12 too was similar to things that we've already done. So I'll let you guys look through this on your own to get the answer for that one. Okay, 13. Yeah, same type of thing. Number 14, let's do this one. A man drags a package across the floor with a force of 40 newtons, and he's on an angle like that. As shown, the mass of the package is 10 kilograms. If the acceleration of the package is 3.5 meters per second, and the friction can be neglected, what is the angle to the horizontal does the man pull? All right. So this one isn't actually as bad as you would think. So if you draw a little triangle there, like what's happening, um, this is the force that we care about, right? The net force, because that's the force that's making this thing accelerate. If I go back to my picture here, if we drew a free body diagram, there would be a normal force up, there would be a force of gravity down. Don't really care, right? They're not contributing to the net force of this thing because they're balanced. So we can kind of forget about those things. The only thing that's responsible for moving this thing is the x component of this, right? That's the only thing, because that's the direction it's moving. It's moving to the right. So that's the only one we care about. So when we do this, we're going to figure out the net force of this thing just by, we know the net force of this one. So right from the question, it tells us that it is 10 kilograms and it's accelerating at this speed. So if we just multiply those together, we get 35 newtons. That is the x component of this triangle. Now that you know the adjacent side and you know the hypotenuse, using your trig identities, we can figure out the degrees right there. Okay, 15. A spring is compressed between two marbles. Then when the spring is released, marble A, and they tell us the mass, is projected from rest to negative 15 meters per second in 0.0350 seconds. So really, we're after an acceleration here, right? They've given us the info for an acceleration of this thing. What is the mass of marble B if it experiences a velocity change from rest to 22 meters per second in that many seconds? Okay. So what we got to do is figure out the force that was applied to marble A, because Newton's third law, the force on FA is going to be equal to the force on FB. For every action, there's an equal and opposite reaction. And it's talking about forces. That this isn't true with like accelerations. I can't say acceleration A is equal to acceleration B because they have different masses. But the forces I can. The forces are equal. So what I'm after is force A, because then once I figure that, that's going to tell me this, right? Because they'll be the same but just different directions. Okay, so marble A, we know the mass. We know V1 is 0. We know V2 and the time. So if we figure out acceleration using this formula, and then use the mass, so acceleration, and then multiply by the mass, we figure out that the force on this thing is negative 8.57 newtons. So if that's negative 8.57 newtons, then the force on B is going to be 8.57 newtons to the right. Okay, now that we know that, all we got to do is figure out the acceleration on this thing, and then we're just really close to knowing the mass. So to figure out the acceleration, we use this formula, just the same as above. Figured out that the acceleration of this thing is 628.6 meters per second. Now we just got to use force is equal to mass times acceleration and rearrange for mass. So mass is equal to 13.6 grams after you convert it from kilograms. And make sure that when you do these formulas too, maybe I didn't explain that enough, that mass, for some, well, not for some reason, when we say force is equal to mass times acceleration, it's the only time I can think of in these formulas that we don't use the base units in these formulas. We use kilograms as the units. And it only works with kilograms. So you can't just put grams in there and get the right answer. If you did, you'd probably get, a funny answer here. It'd be the same numbers, but just the digit or the decimal places would just be off by 3. All right, and that's it for the key.